Okay, STEM chemistry. Sorry about that. We are back with the second portion of this Ideal Gas Laws podcast, where we'll be able to finish up this problem and keep going with the last part. So this one should not take very long. Okay, we finished up here on the last one. It got cut off on you. And I said, hey guys, this is the total pressure of the system. We know that this is the pressure of the water vapor, and they want to know the pressure of the dry gas alone, so just the oxygen gas. So how do we figure that out? Well, we set it up in our Dalton's partial pressure law, where the total pressure of the system is equal to the pressure of the first gas plus the pressure of the second gas plus blah, blah, blah. Well, to solve for the pressure of oxygen, all we have to do is subtract. So if we subtract 23.8 from both sides, the pressure of the oxygen gas alone would be equal to, let's see, 760 minus 23.8. And that would be 736.2 millimeters mercury. And we look at significant figure rules, which is the decimal places, so this stands. And that's all we have to do. Just make sure that you read the problem, because sometimes they give you things like this, and other times they'll give you the conditions, and you have to solve for the pressure, and then you would subtract. Okay, so just make sure you pay attention and read through the question carefully. Okay, movement of gases. So there's different ways that we can describe the movement of gases. We have effusion, which is when a gas escapes from a tiny hole in a container. The smaller the particle, the quicker it will effuse, and that's not necessarily due to the size of the particle. It's actually more based on the mass of the particle and how quickly it's moving. And since mass and velocity are related, okay, because velocity is equal to, let's see this. If you have something that has a bigger mass, it's going to have a slower velocity. And if something has a lower mass, something that's teeny tiny, is going to go a lot faster. So if it has a smaller mass, it moves quicker. So the smaller the particle, the quicker it effuses. All right, so diffusion, on the other hand, is talking about how a gas will spread out in a space that moves from an area of high pressure to an area of low pressure. And this explains why during the holiday season you can walk into somebody's house, or anytime somebody's been cooking, you can walk into their house and you can smell what they've been cooking or what they've been eating without standing in the kitchen right next to the food, and that's because these gas molecules will spread out from an area of high pressure to an area of low pressure, and guess what? The smaller the particle, the quicker it's going to diffuse. Okay, so we can use this thing called Graham's law of effusion, and Graham's law of effusion gives us a rate of effusion of gases at the same temperature and pressure, says they're inversely proportional to the square roots of their molar masses. So if we have the molar masses, we can usually figure out the rate at which they're effusing. You don't have this next one on your paper, just pause it and write it down. Okay, so at a certain temperature and pressure, chlorine molecules have an average velocity of 0.0380 meters per second. What is the average velocity? So we're looking for average velocity of sulfur dioxide molecules under the same conditions. Okay, so this would be our rate, and we know that this is chlorine molecules. Okay, so chlorine molecules have a rate of 0.0380 meters per second, and they want to know what is the rate for sulfur dioxide. Okay, so we go back and we look at that equation. Down here we have the rate of one over the rate of the second one is inversely proportional to the square root of their molar masses. Okay, so I'm going to come back over here, and we know that the rate, let's just do chlorine, over the rate of sulfur dioxide should be equal to the square root of the molar mass of sulfur dioxide. That is a hot mess, sorry. And my pen keeps disappearing. There we go. Divided by, there we go. It's stopping. Okay, sorry. The molar mass of chlorine molecules. Okay, so all we have to do to solve for the rate of sulfur dioxide is we plug these in here. Okay, well the rate of chlorine is 0.0380 meters per second We're looking for that one, so I'm going to put an X there. And here I want to do the square root of the molar mass of sulfur dioxide. Okay, so sulfur dioxide is 32 plus 32.07, which gives us 64.07 for sulfur dioxide, and the square root of the molar mass of chlorine, 2 chlorine molecules, which gives us 70.90. Okay, this is a proportion, so you can cross multiply and divide. If you want to solve it another way, that's fine. I don't care how you solve it. It really doesn't matter as long as you get the right answer. Okay, I'm not going to tell you which way to solve it. All right, so you should end up getting, let me get my answer sheet out here because I've already answered it. All right, the calculator is going to give you 0.0399746 blah, 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 blah. How many significant figures do we want? 3 significant figures. All right, so that one doesn't count, that one doesn't count. 1, 2, 3 significant figures. So all of this is going to round up to 0.0400 meters per second. And that would be the rate of effusion for sulfur dioxide molecules at the same conditions as the chlorine molecules. All right, so does that make sense? Well, let's look at them. Okay, chlorine and sulfur dioxide. We're just doing a quick comparison. Okay, so chlorine molecules have a molar mass of 70.90 grams per mole, and sulfur dioxide has a molar mass of 64.07. Just looking at those two, which one should go faster? The sulfur dioxide. Why? Because it's lighter. Okay, because it's lighter. Okay, so let's look at their rates. The rate of effusion for chlorine is 0.0380 meters per second. The rate of effusion for sulfur dioxide is 0.0400 meters per second. Which one's going faster? Sulfur dioxide. Does it make sense? Yes. Why? Because it's smaller. Okay, that's all you got to do with that. And I think that's it. That's it. Okay, so I guess I'll see you in class.